we venture forth into the cosmic expanse on a journey of discovery, prodding at the edges of reality itself. What if the cosmos in all its grandeur is not what it seems? Could our universe be an illusion, a sophisticated facade veiled by the complex laws of physics? Our exploration leads us next into the labyrinth of time, an elusive element that persists relentlessly across the universe. Time stretches, compresses, and threads all aspects of existence together. It acts as an invisible link, connecting the past, the present, and the uncertain future, shaping the very framework of our reality. As our journey reaches its zenith, we confront two formidable pillars of our understanding: the speed of light and the enigmatic force of gravity. The speed of light, a boundary that defines the possible from the impossible, and gravity, an unseen force that dictates the interactions between all matter, bending the very fabric of space and time. Through these, we attempt to decipher the cosmic code that governs our universe. Buckle up for a voyage into the cosmic unknown, where we deconstruct and challenge our understanding of the universe, guided by the principles of time, light, and gravity. Absolutely everything around us, even ourselves, is a part of our universe. We're used to thinking of it as something ephemeral, but what is the universe really like? Today we're going to challenge everything you know about the universe. What if everything we see and feel is just an illusion? Well, hold on tight, because we're about to dive into the mysteries of the universe itself. First, let's look at what we know about our universe. The paradox of how our universe came to be is still a mystery to scientists. As far as we know, 13.8 billion years ago, according to the Big Bang Theory, the universe emerged from a single singularity in which all the fundamental forces were united. On the other hand, according to the Hawking-Hartle theory, the universe did not begin to exist from a single point. It existed as pure space without time, which appeared later with the Big Bang. Despite the difference in modern ideas about the formation of the universe, at one point, cosmic inflation began, resulting in the formation of protons and neutrons in a microsecond, which combined into basic building blocks such as hydrogen and helium. And then, after cooling, in 360,000 years, light, and millions of years later, stars and galaxies. We can still observe other galaxies moving at high speed as a consequence of the expansion through the Big Bang. So, 1 billion years after the explosion, the universe was formed as we see it now. However, what do we mean when we talk about the universe we observe? The part of the universe that we see is probably not very big. Actually, it's about 93 billion light years across. What each of us sees is the matter and energy that fills the cosmos. Oddly enough, the percentage of normal matter that makes up stars and planets is very small compared to the hypothetical dark matter, which we've not yet been able to detect. However, the most exciting thing we know about the universe is life. According to the principles of physicist Brandon Carter, we exist as observers, and the universe is compatible with our existence, and the universe must exist in such a way that it has observers. That is, the universe exists in such a way that our existence is possible. This leads to a fundamental question: does the universe exist without us? Let's turn to quantum theory. The physicist John Wheeler, a colleague of Albert Einstein, believed that human observations in the present could influence the behavior of photons in the past. The well-known experiment with two slits and a beam of photons directed at a screen demonstrates that observers with detectors can influence the behavior of photons. Thus, if there are observers, the photons behave like particles and pass through one of the two slits. However, if there are no observers, then photons begin to behave like waves and pass through both slits at once. Wheeler decided to transfer this experiment to the cosmic plane, replacing the photon gun with a quasar and the slits with two galaxies nearby. Thus, the photon, which could have started its journey even billions of years ago, even before the origin of life and the development of photon detectors, is forced to move towards these detectors. That is, the movement of light always depends on observers. So it turns out that the universe cannot exist if there is no human? Not quite. Indeed, humans are capable of absorbing information, analyzing it, and reproducing it for others, but they are not, albeit perfectly, the only observer. Following Wheeler's example, a high-energy particle, which can also exist in different states, can interact with stones on the ground. Thus, the stones will leave a trace of the particle, meaning that a new certain exchange of information has taken place. Therefore, according to this assumption, the universe does not need consciousness to exist. This confirms another experiment in quantum mechanics. Most recently, a trio of scientists who shared the Nobel Prize, John Clauser, Elena Specht, and Anton Zeilinger, were able to prove that the universe is not real locally. This, of course, does not mean that the universe as we know it does not actually exist. Physics distinguishes between the principles of reality and locality. Reality means that an object exists and does not change its properties even if no one observes it. A red apple will remain red, with or without measurements. Locality, in turn, can be explained by the fact that objects can affect each other only if they're in contact with each other, and that distant bodies cannot affect each other instantly or at the speed of light, for example. If you send a light signal to your friend 10 light years away, you will not receive a response as soon as you turn on the flashlight. This leads to the principle of local realism or hidden variables, according to which objects that have certain properties that exist at some imperceptible level and do not depend on observations. In other words, we live in an objective reality with a specific set of factors that do not depend on our consciousness. However, physicist John Stuart Bell disagreed with this. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published an article under the acronym EPR, in which the theorists tried to prove that quantum physics was absurd. They questioned the possibility of quantum entanglement. If two particles are entangled, then their connection is preserved even if they are in different parts of the universe. For example, if a particle rotates clockwise around itself, the other particle with which the former has a connection will rotate counterclockwise. Thus, if one particle is on the Earth and the other is at a distance 1,000 light years, then knowing the direction of rotation of one, you can immediately find out which way the other is rotating. And this contradicts GR because nothing can move faster than light. So, 30 years after the publication of EPR, Bell conducted a thought experiment. He continued the idea of EPR but improved it a bit. He imagined two observers, Alice and Bob, who are in different parts of the solar system and have particle detectors, but with two different settings. A, and B, for a more accurate test. So if the theory of local reality were true, then one particle could not know what parameters the other has. The results are always random, and if quantum theory is true, then the particles will be perfectly correlated. 3 Nobel Prize winners, Clauser, Specht, and Zeilinger, were able to repeat the experiment in reality. By counting the number of times Bob and Alice agreed with each other about the state of the particles, they confirmed Bell's theory, proving that the universe is not locally real, meaning that it really needs an observer for everything in the universe to exist. So you can exhale. The universe exists as we imagine it. However, what if I told you that this may not be the case at all and that our brains are deceiving us? From our perspective, according to Einstein's GR, the universe is a space-time continuum with 3 spatial and 1 temporal dimension. All the massive objects in our universe, like our Earth, can curve this space-time, which is the cause of gravity. Yes, we do observe all of this. So what could be the deception? Perhaps our 4-dimensional universe could be a holographic projection. It sounds too fantastic, but this theory is actually being seriously considered by scientists. Everyone has probably seen a hologram, a deep 3-dimensional image created on a flat surface using light. The light that creates holograms contains a lot of encoded information, such as texture or relative distance. So from all points of view, the image will appear 3-dimensional. Theoretical physicist Juan Maldacena, he suggests that our universe could be like this. Everything we see as 3-dimensional happens in 2-dimensional space. Black holes contributed to the development of this idea. Black holes can increase their mass at the expense of other objects that fall into them. But these objects do not disappear, they remain in the black hole. However, black holes can decay. The famous physicist Stephen Hawking discovered that black holes evaporate and subsequently can completely disappear. What then happens to the information that fell into the black hole? Will it disappear forever? This is contrary to the fundamental laws of physics because matter cannot be destroyed. It changes into another state according to the principle of the conservation of mass. However, the idea of the holographic nature of the universe can resolve this paradox. The holographic theory is explained through a hypothetical duality between 2 other mathematically equivalent theories, the ADS-CFT correspondence. Anti-de Sitter space, ADS, is a space with a negative space constant that's closely related to string theory, such as one that has a curved parabolic shape in more dimensions than string theory requires. This space is mostly defined as 5-dimensional, but its number of dimensions can reach 10. ADS also has a boundary, unlike the more popular model of the universe. Modern cosmology proposes a model of a flat universe, similar to an ordinary sheet on which 2 lines or 2 waves of light will always be parallel. If the universe is really absolutely flat, then it may not have any boundaries. However, it is possible that our universe may be curved on an unimaginable scale, so satellites cannot see it. So the ADS can be imagined as 3-dimensional ball, the surface of which will be the boundary, but it's completely flat. This theoretical boundary is crucial for the second theory, conformal field theory, which exists on this boundary. CFT explains the behavior of particles and fields in flat space and has 1 less dimension than ADS, and in particular, no gravity. Because of this, a duality arises that allows us to look at the system from 2 sides. What happens in ADS inside can be translated into CFT and vice versa. Therefore, their duality is similar to a hologram on the border, which encodes everything that's inside. Thus, according to ADS-CFT, information that falls into a black hole does not disappear without a trace. The information can be encoded in the 2-dimensional event horizon of the black hole, beyond which the gravitational distortion becomes so strong that even photons cannot escape. Therefore, the information does not disappear but is simply copied to the surface. This duality theory explains this and other modern mysteries of the universe well, but it has several problems. For example, The ADS-CFT correspondence works in the model of the universe with a negative cosmic constant. However, according to modern observations, our universe has a positive value for the constant and continues to expand. So we probably do not live in a curved, finite universe. For example, in 1929, astronomer Edwin Hubble concluded that the universe continues to expand and this process may continue forever. Therefore, the question of the infinity of the universe is open due to the limitations of our observation. This point is crucial for the whole theory. So for now, the idea of ADS-CFT has value from a mathematical point of view, but if we manage to find answers to all the mysteries of the theory, then perhaps we can confirm that our universe is a hologram. The question of what our universe is has been a concern not only for physicists, but also for philosophers. In 2003, philosopher Nick Bostrom proposed an idea that some scientists, like Elon Musk, consider to be somewhat possible. What if we are living in a simulation? In his article, Bostrom believed that one of his claims about the probability of simulation must be true. First, humans will die before they reach a technological level that would allow them to create highly complex simulations. And two, it is extremely unlikely that an advanced civilization will be interested in simulating its history. Three, advanced civilizations create simulations and we live in one. So if the third idea is true, then we can live in a fully simulated world, just like in any computer game. Of course, it's impossible to empirically test this hypothesis, but we probably have some evidence to support the simulation hypothesis. It's the speed of light. According to Einstein's theory, we know very well that light has a limited speed, 186,000 miles per hour. So all the light we see from the stars reaches us with a long delay. The device on which the simulation is created cannot have infinite computing capabilities. There must be a limit. And it's precisely the artifacts of this limit that we can see in the limitation of the speed of light. So if this hypothetical computer processor running the simulation could perform one operation per second, its memory capacity would be 186,000 miles. In particular, the simulation can also explain the principles of quantum mechanics. As with subatomic particles, we determine their state when we look at them. So based on the simulation hypothesis, we only see a rendered part of the universe's graphic, while the rest of the graphic remains unloaded. And yet, despite the interesting explanation of the light speed limit, the simulated universe is considered a speculative hypothesis because it can be neither refuted nor confirmed. Perhaps someday we will return to this idea if the matrix of that hypothetical computer starts to malfunction. So the universe is still a giant mystery to us. We can't even be sure if everything we see is not an illusion. As we said, we are crucial to the universe as outsiders, but what if we're never really meant to exist? It turns out that Earth, the Sun, and our galaxy were never meant to exist. Scientists at CERN have suggested that after the Big Bang, perfectly symmetrical matter and antimatter should have been created equally. So if this scenario had happened, all particles would have combined with each other, destroying absolutely everything. However, something has caused an imbalance between both types of matter, and it's not yet known what it is. So we can say that we're lucky because right now we're here, and we can not only observe the universe, but also reveal all of its secrets. Do you think it could be that one of the most fundamental aspects of our lives is nothing more than a complex illusion? Time, the omnipresent force that apparently governs our existence and dictates the rhythm of our lives, is not what it seems. For example, time appears to be slowed down for an object moving close to the speed of light, and it flows at different speeds depending on the strength and the gravitational field around us. Have you ever considered that time may be just a figment of our imagination, a construct invented by our brains to make sense of the world? In search of the truth behind this mysterious concept, you'll have to step into the unknown and question everything you thought you knew about time. Time, in its simplest form, is a tool we created to measure change and put order into the complex events that make up our lives. Our ancestors needed a way to keep track of natural cycles such as day and night or the changing of the seasons. This was crucial to the coordination of activities such as farming, navigation, and religious rituals. Early methods of timekeeping were based on natural phenomena such as the rising and setting of the sun, the phases of the moon, and the position of the stars. As human society became more complex, so did our methods of measuring time. We developed tools such as sundials, water clocks, and finally, mechanical clocks to divide the day into smaller and more manageable parts. Calendars were created to track the passage of longer periods such as months and years. Different cultures have developed their own unique calendars and timekeeping systems, reflecting the diversity of human understanding and interpretation of time. While timekeeping systems help us manage our daily activities and long-term planning, the perception of time remains a deeply personal and subjective experience. Our brains process and interpret time differently depending on factors such as age, emotional state, and cultural background. This suggests that time is not a specific universal phenomenon, but rather a flexible construct that we shape according to our individual experiences and needs. Despite its ubiquitous presence in our lives, time remains a somewhat illusory concept. This raises the question: is time an objective reality, or is it simply a construct we've created to order the chaos of our existence? So let's delve a little deeper into history. The traditional understanding of time as an independent, constant entity was challenged by a groundbreaking work from the early 20th century written by Albert Einstein. Einstein's theory of relativity introduced the concept of time as a dimension, forever changing our view of this mysterious phenomenon. Einstein's theory of relativity emerged from his work on the nature of light and the concept of absolute space and time, which was central to classical physics. He proposed that the law of physics should be the same for all observers, regardless of their motion relative to each other. This revolutionary idea led to the development of two interrelated theories: the special theory of relativity and the general theory of relativity. In the special theory of relativity, Einstein demonstrated that space and time are not separate entities, but intertwined in a single continuum known as space-time. In this four-dimensional structure, time becomes the fourth dimension, and events are represented as points in space-time. This concept shattered the traditional view of time as an independent variable by showing that it is an integral part of the fabric of the universe. Einstein's theories also showed that time is relative and dependent on the observer's frame of reference. According to the special theory of relativity, two events that appear to be simultaneous to one observer may occur at different times to another observer moving relative to the first. This phenomenon, known as simultaneity relativity, challenges our perception of time as an absolute and constant entity. The general theory of relativity extended the ideas of the special theory of relativity to include gravity in the picture. In this theory, massive objects such as planets and stars cause space-time to warp, and this warp is perceived by objects moving within it as gravity. The presence of a massive object can also affect the flow of time, leading to a phenomenon known as gravitational time dilation. In the special theory of relativity, time dilation occurs when two objects move relative to each other with considerable speed. The faster an object moves, the slower time flows for that object compared to a stationary observer. This effect becomes more pronounced as the object approaches the speed of light. This phenomenon is best illustrated by the famous twin paradox, where one twin travels at near the speed of light, while the other stays on Earth. Upon return, the traveling twin will be younger than the Earth twin because of the time dilation. In general relativity, time dilation is also due to the influence of gravity. Time flows more slowly in stronger gravitational fields, for example, near massive celestial objects such as planets or stars. This effect has been experimentally tested using atomic clocks placed at different heights. Clocks closer to the Earth's surface, where gravity is stronger, run slower compared to clocks at a higher altitude, where gravity is weaker. The slowing of time, while seemingly illogical, has been confirmed experimentally and has practical applications. An excellent example is the Global Positioning System, or GPS. GPS satellites orbiting the Earth experience time dilation based on both velocity and gravity, which must be taken into account to maintain accurate timekeeping and location data. In addition, experiments with high-speed particle gas pedals have confirmed that particles traveling at near light speeds experience significant time dilation, as predicted by the special theory of relativity. Before Einstein's theory of relativity, time was assumed to be unchanging and a universal background for all events in the universe. Sir Isaac Newton, for example, believed in the concept of absolute time, which flows uniformly and independently of the events he measures. However, the discoveries of time dilation and the relative nature of time in both the special and general theories of relativity challenge this concept, demonstrating that time is not a constant but a variable, depending on the motion of the observer and the surrounding gravitational field. The traditional view of time as an absolute entity also assumes a strict adherence to causality, where cause always precedes effect. However, the relative nature of time in relativity theory suggests that the order of events may depend on the observer's frame of reference, which can lead to situations where cause and effect may appear to be reversed or simultaneous. This challenges our intuitive understanding of causality and forces us to re-evaluate how we think about the evolution of events in the universe. The concept of the arrow of time, the idea that time flows in one direction from past to future, that's deeply rooted in our understanding of the world, has also been challenged. However, the findings of relativity theory regarding the relative nature of time and the potential reversal of causality prompt us to reconsider whether the arrow of time is a fundamental aspect of the universe or simply a construct of human perception. Since the traditional view of time as an absolute entity has been undermined by the discoveries of the relativity theory, some scientists and philosophers have suggested that time may be an emergent property rather than a fundamental aspect of the universe. From this perspective, time arises from interactions and relationships between objects and events, rather than existing independently. Leaving behind the challenges of Einstein's theory of relativity, we venture into the even more confusing world of quantum mechanics. In this realm, the nature of time becomes confusing and elusive, as the rules governing the quantum world defy our everyday understanding. Quantum mechanics is a branch of physics that studies the behavior of particles at the atomic and subatomic levels. It's governed by a set of probability rules that are markedly different from the rules of classical physics. In the quantum world, particles can exist in several states simultaneously, a phenomenon known as superposition, and their properties are defined only when they're measured or observed. The concept of time in quantum mechanics is very different from the concept of time in classical physics. While classical physics described time as a continuous and absolute entity, quantum mechanics treats it as a discrete, quantized parameter. This leads to situations where it seems that time loses its traditional meaning and takes on a more abstract role. Now, to illustrate, let's consider the following everyday scenario. You observe animals in the wild and notice they behave differently when they know they're being watched. The closer you get to them, the more their behavior changes, making it difficult to understand their natural state. This example illustrates the observer effect in quantum mechanics, also called the Heisenberg uncertainty principle. In the context of quantum mechanics, the observer effect refers to the idea that active measurements or observations can disturb the state of a quantum object, such as an electron. Just as your attempt to observe animals in the wild affects their behavior, observing or measuring a quantum object can affect its properties, such as position or momentum. Heisenberg's uncertainty principle states it's possible to simultaneously know the position and momentum of a quantum object with absolute accuracy. The more precisely we measure one property, the less precisely we can know the other. In the quantum world, the very act of observation or measurement can lead to the collapse of the wave function of a particle and the transition from the superposition of many states to one definite state. This process is inherently probabilistic, and the result cannot be predicted with certainty. Taking into account the phenomena of quantum superposition and observer effect, it becomes obvious that our traditional understanding of time as linear progression may be wrong on the quantum level. Instead, the quantum world offers a more fluid, interconnected view of time where the boundaries between past, present, and future are not as rigid as we once thought. As we've seen, our understanding of time is closely intertwined with our understanding of space. And this complex relationship has given rise to many theories attempting to explain the nature of space-time. Among these theories, one stands out as particularly intriguing and thought-provoking: the block universe theory. The block universe theory, also known as eternalism or the space-time block view, is a philosophical concept that stems from our understanding of Einstein's theory of relativity. According to this theory, past, present, and future are not separate entities, but part of a single four-dimensional structure called space-time. In this structure, all events from the origin of the universe to its possible end coexist simultaneously. To better understand the theory of the block universe, we must first understand the concept of space-time. In Einstein's theory of relativity, space and time are intertwined, forming a single continuum. Space-time can be thought of as a vast four-dimensional block containing every event that has ever happened or will happen. In this situation, time is not a separate dimension that flows linearly, but rather an integral part of the space-time structure. Each point in space-time represents a unique event, and all space-time encompasses all possible events. Consequently, past, present, and future coexist in a block universe, turning our perception of time as a linear progression into an illusion created by our limited perspective. In the block universe theory, observers play a crucial role in the perception of the flow of time. Our perception of time as a linear progression from past to present to future is the result of the movement of our consciousness along our world lines, the paths we trace in space-time. Although all events exist simultaneously in the block universe, our subjective sense of time is limited to a single point on our world line, the present moment. This subjective sense of time can be likened to reading a book. Although all the words and sentences exist simultaneously on the pages, our perception of history is sequential, revealing one word at a time. Similarly, the events of our lives unfold as we cross our world lines with the block universe. Block universe theory also raises thought-provoking questions about the nature of free will. If all events, including our thoughts, decisions, and actions, are predetermined and exist simultaneously in space-time, does this mean that our choices are predetermined and free will is an illusion? This question has been the subject of heated debate among philosophers and scientists alike. Some argue that the existence of free will is compatible with the block universe theory, since our choices can still be determined by our internal processes, even if the results are already fixed in space-time. Others argue that a block universe implies a deterministic universe where our actions are simply the result of the laws of physics and the concept of free will is an illusion. Not only does the theory of the block universe challenge our understanding of time and causality, it also raises profound questions about the nature of reality itself. If all events coexist in space-time, does this mean that reality is a static, unchanging structure? Or is our perception of reality, including the subjective flow of time, an essential aspect of the universe that cannot be separated from the objective structure of space-time? These questions go to the heart of our understanding of the nature of existence. By exploring the implications of block universe theory, we may be forced to reevaluate our perceptions of time, causality, free will, and reality itself, opening the door to a new understanding of the fundamental nature of the universe. In our daily lives, we rely on the passage of time to structure our activities, make sense of the world around us, and create meaningful accounts of our experiences. Time allows us to perceive change, growth, and decline, and to make predictions guided by past events. At the same time, our study of the nature of time has shown that our perception of time as a linear progression may only be a simple illusion, the product of our limited perspective in the vast fabric of space-time. This paradoxical nature of time is a fascinating enigma. Time is both an important aspect of our lives and a construct that may not exist as we perceive it. Either way, we must remain open to new ideas and perspectives, for it's through our curiosity, our willingness to question the nature of reality, and our relentless pursuit of knowledge that we will continue to discover the mysteries of time and the universe itself. The speed of light is one of the most fascinating and mysterious concepts in the universe. It's considered the cosmic speed limit, beyond which nothing can move faster. However, what if I told you that it's possible to reach this incredible speed? While it may seem impossible, the laws of physics make it possible. In this video, we'll explore the fascinating world of the speed of light and how you can get closer to this incredible speed. So fasten your seatbelts and get ready for a journey into the unknown as we explore the limits of what's possible in the universe. First, let's recall what speed is and how light works. So in physics, we call speed a certain value equal to the distance an object travels in a certain time without an exact direction. When an object moves, it increases its mass and the level of its kinetic energy. So the faster it moves, the more mass it will gain and its energy will increase. Therefore, for example, the faster a space rocket moves, the greater the scale of destruction if it collides with a meteorite body, and the more energy will be consumed. In particular, objects can change their speed depending on the medium and its molecular composition due to friction. So this all works for objects that have mass. But what about particles that have no mass, like photons? Let's turn now to what we know about light. Light is an electromagnetic wave resulting from the emission of energy from heated bodies that are perceived by our eyes. However, light is probably also a wave and can be described as a stream of massless particles or quanta photons. Light has a speed of 186,000 miles per hour, and in a cosmic vacuum, it's the likely speed limit for the entire universe. This is what Albert Einstein's fundamental work, which changed the way we understand our universe, tells us: general relativity. If we summarize this theory in one sentence, its main idea is that gravity is a curvature of space, not a force that acts on all objects, and the laws of physics apply equally everywhere. But what does this have to do with light? According to GR, light is constant. That is, it always has the same speed and is probably the fastest phenomenon of all. The reasons for this are the absence of mass of photons and the absence of light moving along the timeline. According to GR and the parabolic model of Hermann Minkowski, Einstein's teacher, time is unified, meaning that there are no separate time and space. Our universe has 4 dimensions: 3 spatial, x, y, and z, and a temporal, t, dimension. Since space is one, everything in it is interconnected. Therefore, depending on your location in space-time, you interact with time and space differently. Let's imagine this using a simple coordinate system with a time and space line. If you're sitting here watching this video, for example, you are moving only in time. Your position in space does not change and you have no speed at all. However, if you decide to go to the store, then you'll be moving in both time and space. It's precisely because of the fabric of space-time we cannot synchronize watches because of the time dilation. This was also proven by scientists in 1971. The researchers placed hydrogen clocks in airplanes on the ground and flew around the world. After landing, it turned out the clocks on the airplanes were running slower by about 1/1,000,000th of a second. Light, on the other hand, moves only in space. It does not feel the influence of time, so if we were to put a clock on it, it would seem to be suspended. Moreover, since light has no mass, it's not affected by gravity. However, if it passes near a black hole or a star, or more precisely along the geodesic lines of space-time near a massive body, its path and energy consumption increase and curve, but its speed remains constant. So if the speed of light is constant and photons are not affected by time, especially in space, how can we achieve or even surpass it? An object with mass, like you and me or a spacecraft, cannot move at the speed of light because it would require infinite energy. However, interestingly, there is another reason. We are already moving at the speed of light. We learned this from Minkowski's model. The faster we move, the slower our clocks go. However, since we have mass, time affects us and we're not physically moving at the speed of light. Our speed is scattered between time and space. Even charged particles cannot reach the speed of light because they also have mass. Scientists are trying to accelerate subatomic particles to the constant of light using linear accelerators with the help of an electromagnetic field, but their speed is always 99.99%. However, at the end of the 20th century, scientists discovered a strange phenomenon, namely the so-called FTL, the movement of particles several times faster than photons. Thus, while observing the galaxy M87 and its jet, a beam of ionized matter ejected from galaxies at high speed. A group of researchers took several pictures of the jet. They noticed that the jet seemed to be moving faster than light. However, this is probably just an optical illusion caused by photons that were emitted later from almost the end of the jet. So it seems to us the light from it travels a shorter distance. Moreover, there's another phenomenon in space that can accelerate particles to the speed of light, but this time it is true: magnetic explosions. When magnetic fields collide with each other, they can often become entangled. If the tension between them increases greatly, they will break apart, which will throw all the charged particles away in an ultra-high speed. This process can be considered a natural particle accelerator. However, this is all about measurements in a vacuum. Recall that light travels through a certain medium, such as water, more slowly than in a vacuum. So charged particles can move faster than light, but in some kind of medium. The proof of such FTL motion is Cherinkov's irradiation. When a particle moves faster than light in some medium, it polarizes other particles, or in other words, it repels or attracts. When the charged particle moves further, the electrons are returned, which causes the butte glow of the irradiation. One hypothetical subatomic particle could be another competitor to light in speed. In 1962, scientists considered the possibility of the existence of particles that would be faster than light with the inclusion of GR. But in their work, they noted that such particles could move faster than light from the moment of their appearance and not by increasing their speed, which is not contrary to GR. These theoretical particles were called tachyons. Unlike other particles, a tachyon has energy, but its mass at rest is imaginary, meaning it has a mass only when moving faster than light. It's also likely that an approaching tachyon will be invisible because light travels slower than it. In particular, it's also hypothesized to speed up when it loses energy. It's believed that a tachyon is formed when energetically strong cosmic rays hit the Earth's atmosphere. So far, the existence of tachyons has not been confirmed, and therefore light can be considered the speed limit at the moment. In addition, tachyons can lead to logical temporal paradoxes. For multiple observers, a tachyon can travel to the future and the past. So, if a tachyon can travel back in time, this leads to the classic causal paradox, for example, in which a traveler can affect his own existence and prevent his own birth or send a message to himself in the past. However, does superfast motion really lead to traveling back in time? In fact, faster-than-light travel is not necessarily the cause of paradoxes. For one observer, a spacecraft whose speed exceeds the light constant will travel back in time, so it will also land in the past before it took off. However, according to the physicist Sabine Hossenfelder, such paradoxes are possible from the standpoint of special relativity, not GR. Thus, another observer, for example, can move along with matter in the same direction, forward in time, which means that the ship for him moves only forward, and therefore cannot break the causal relationship and first land and then only take off. In fact, the second observer follows the entire process, and therefore does not see any logical violations that arrive from the perspective of the first observer, who believes that the ship is moving backward. So we can't simply accelerate to the speed of light. However, we know that light travels in space-time. What if we could bend space so that light travels a longer way than the object around which space is deformed? It sounds fantastic, but scientists are considering this space travel option. This concept is called the Alcubierre drive or warp drive. The idea of a warp drive is to stretch the canvas of space into a wave which should hypothetically compress the space in front of an object, such as a ship, and expand the space behind it. Thus, the ship will essentially move on this wave in a so-called warp bubble faster than light. Alcubierre's drive consists of three parts: the inner bubble or passenger space, where time passes more slowly than in the general space, and two outer parts, a shell of negative and positive energy and normal space without changes. However, warp drive requires a conceptual negative energy, which is impossible according to GR, but can exist in quantum theory in small quantities. This is one of the main problems of this theory. So to be able to implement it, it is desirable to find a method using positive energy. In 2021, astrophysicist Eric Lentz was able to develop such a concept. According to his model, such a bubble should contain a liquid plasma with a huge mass, about 10% of solar energy, and electromagnetic fields that would be located around the ship in the shape of diamonds. Such a bubble would be able to transport the ship, but only at a speed close to the constant of light, meaning that such a drive would not be able to accelerate to FTL. So far, it's impossible to confirm whether warp drive can exist without negative energy, as well as to start experimental work on it in general. However, if warp drive can work without the use of negative energy, then in the future, we'll be able to travel to distant planets much faster than with current technology. Another way that negative energy could hypothetically allow us to travel in time actually faster than light is through Einstein-Rosen bridges or wormholes. Einstein first came up with the idea of the existence of such tunnels from one place in space to another. It's believed that wormholes can be connected at gigantic distances of several million light years. However, although they have not yet been found, wormholes are very unstable, so they can quickly disappear due to negative energy. In addition, they're probably not as wide as we imagine. Also, because of this energy, wormholes must be too small for a person to pass through. Therefore, until scientists find a way to keep both wormholes stable and large enough to confirm their existence, we cannot use this method for travel. Finally, quantum physics offers an interesting hypothetical way to transmit information at speeds greater than the light constant. This method of FTL communication is called quantum entanglement. In fact, quantum entanglement is an inseparable combination of two quanta that can exchange information with each other faster than light, despite the distance. Particles communicate by changing their state, for example, by changing their spin or energy. So during a long-distance travel in space, hypothetically, an astronaut could send a signal about possible life on the exoplanet under study, and this signal would reach the controller almost instantly. However, in reality, it is their variability and randomness that's the main problem that makes this concept of FTL information exchange unlikely. Quanta cannot be brought into a certain state to transmit any data because then the particles will break the connection with each other, and the particle whose state has not changed would show random results. So communication in this way would be impossible and probably not even reach the speed of light, because information cannot be transmitted at a speed greater than the light constant according to quantum mechanics. Moving at the speed of light or even faster gives us a serious advantage in space exploration. At the moment, we're not able to achieve this speed, but the hypothetical ideas of warp drive and tachyons, as well as the use of knowledge about FTL in different environments, can be an important step towards further research into ways to achieve the light constant. However, this is still in the distant future, so our priority now is to develop the technical knowledge we have so that our main goal in the study of space-time will be speed. In a world where gravity is taken for granted, we decided to unravel the hidden truths that lie behind the scenes. Get ready for us to delve into the mysteries that defy our understanding. What if the essence of gravity as we know it is nothing but an illusion? Today, we will dare to challenge everything you think is true. Together, we'll penetrate the veils of perception and uncover the mysterious secrets hidden at the very core of the fundamental principles of gravity. We owe our understanding of gravity as a force of attraction to Sir Isaac Newton. In the 17th century, according to a very popular legend, Newton was watching an apple fall in an orchard. He noticed the apple fell exclusively downward, as if under the influence of a certain force, which inspired him to create the universal law of gravitation. What does this law describe? A conventional apple gains speed as it falls. The apple, like everything else on the planet, has a mass, but it's much less than the mass of the Earth, According to Newton, the force of attraction between the Earth and the apple directly depends on their masses and is inversely proportional to the square of the distance between them. To make it even shorter, all objects with mass and energy are attracted to each other and are in a state of free fall in relation to more massive bodies. This is all expressed in a well-known formula. The formula is broken down as gravitational force, the mass of the primary, mass of the secondary, divided by the orbital radius squared. By the way, Newton tried to model gravity as a field that surrounds all material bodies. This mental model is still used to explain the gravitational interaction between all objects. According to Newton's third law of motion, the Earth should also move toward the apple since it also has its own field. But it's very small and we cannot feel it, which can be explained by Newton's second law, F equal ma, since it's impossible to get the same acceleration for objects with different masses even with the same applied force. However, it was not all bad news. Newton suggested that gravitational force may also affect space bodies, including the Moon. In addition, the satellite has not yet fallen to the Earth's surface, not only because of its constant rapid orbital motion, but also because of the gravitational interaction, which is less between massive objects located at a considerable distance from each other. Newton was able to explain the dependence of the planet's rotation around the Sun due to the gravitational force between them with an imaginary experiment. If you put a cannon on a mountain and shoot a cannonball horizontally, it will fall vertically to the Earth after flying a short distance. But if you shoot it with a very high force, for example, up to 4,500 miles per hour, the cannonball will always be in a state of free fall and will not reach the surface. According to Isaac Newton, this is the state in which our Moon, and in particular all other planets, even outside the solar system, are located. This is how Newton came to the conclusion that gravity is a universal force for the entire universe, acting in the same way everywhere. Moreover, Newton's law did not contradict but complemented other relevant laws. For example, the three laws developed by Johannes Kepler, and they explain the movement of planets in outer space. The law of gravitation can be derived from each of Kepler's laws. Thus, according to Kepler's first and second laws, the orbit of each planet around a star is an ellipse, which means the distance to the planet to the star is constantly changing, including at the closest point from the planet to the Earth, perihelion, and the farthest point, aphelion, where the planet travels the same distance in the same time. Newton's law describes the acceleration of massive objects with respect to the distance to the star. In particular, the third law, which explains that an increase in the orbital radius affects the period of rotation, is also explained in the same way. Moreover, the force that keeps the planets in orbit is proportional to the product of the masses of the Sun and the planet and inversely proportional to the square of the distance between the two space bodies, just as it is between objects on Earth. However, Newton's law could not explain several important scientific observations. For example, Newton's theory explained the motion of the planets around the Sun well, except for one, Mercury. You may remember that Mercury has a strange oval orbit, but that's not the strangest thing. Its closest point of convergence is always in different places and moves slowly around the Sun. This process is called precession. Although this phenomenon is characteristic of all planetary orbits, it's most obvious and surprising in Mercury. The precession of Mercury's orbit is 5,600 angular seconds per 100 years when observed from Earth, but the actual precession time of the planet is 5,557 seconds. Now, those lost 43 seconds cannot be explained by Newton's theory. However, all of this and much more can be confirmed by another theory that is considered fundamental to modern science, Albert Einstein's general relativity. Almost 300 years after Newton's revolutionary discovery, Einstein introduced the world to his view of the concept of gravity in the general theory of relativity. GR was preceded by the special theory, in which Einstein described that space and time should be perceived as an inseparable phenomenon, such as absolutely everything in the universe moves simultaneously in time and space. According to GR, he explained that massive objects are capable of curving time and thus affecting other objects around them, and this curvature is gravity. While Newton's theory was based on a falling apple, Einstein imagined a person in a falling elevator to explain his idea. As he falls, he doesn't feel his weight, because both his body and the elevator are falling at the same speed. However, when the person is moving up in the elevator, he feels accelerated, and it seems that the floor is resting on him. However, if there are no windows in the elevator, then the person will not be able to tell what he or she is experiencing from his or her point of reference. Falling in a gravitational field or moving at a constant speed in a small region of time. In Einstein's theory, this is called the principle of equivalence. In fact, if according to Newton's law, a person falls down due to gravitational force, then according to Einstein's theory, it's due to the absence of a force that pushed the person up. That is, a person is affected by the force generated by the elevator floor, but it is not gravity. This also implies that we are always in a state of acceleration unless we're in a state of free fall or inertial motion from our point of reference. So then Einstein concluded that gravity and acceleration are one and the same, and therefore we're in a state of free fall until an obstacle appears in our path, which became the basis for understanding that gravity is not a force. This is a very unexpected statement. Let's take a closer look at the theory of relativity. So as we've already noted, according to Einstein, gravity is a geometric curvature of a four-dimensional time-space. Its property is not a force acting in space. One can simplistically try to imagine time as a two-dimensional drawn fabric in which massive objects like the planet and sun create funnels, but this is not quite the right idea. A better option is to imagine time as a three-dimensional grid consisting of lines geodesics along which planets move in free fall. They are massive enough to distort the lines along which any objects move. That is why it may seem to us that, for example, cosmic bodies are attracted to each other. The theoretical physicist John Wheeler explained this idea quite simply. Space-time tells matter how to move, matter tells space-time how to curve. We can't see the curvature directly, but we can see the effect of Einstein's gravity. For example, if the crew on the ISS is flying right next to the Earth, they will move in a circle due to the curvature, although from their perspective it will seem they are moving straight. But a large object prevents them from moving in lines. Furthermore, we can observe this on Earth. If two people move from a considerable distance to the North Pole, they will meet as they approach it. No force would act on them. They would simply follow curved lines due to the sphericity of the Earth. Same is true for light. Newton assumed that light is also bent by the gravitational force of massive bodies like all other objects, so the actual location of a light source like a star is different from what we see. However, modern science knows that light has no mass, so how could it be affected by large cosmic bodies? Einstein in turn expanded that light, like you and I, it moves along the same lines of geodesy. Since according to GR, the lines around heavy objects are deformed, light changes its course, meaning gravity does not act on the light itself. However, Einstein's calculations proved that the angle of light deflection was almost twice as large as according to Newton. Einstein's idea was confirmed by astronomers Arthur Eddington and Charles Davidson while observing a solar eclipse in 1919. They compared the actual location of the stars with the light captured in the photographs and were able to confirm that the angular deviation is indeed approximately 1.75 angular seconds as calculated by Albert Einstein. In particular, GR can also answer the question about the strange orbit of Mercury, since, according to its calculations, the planet's orbit is shifted by 43 angular seconds due to the curvature of space. In addition, another proof that gravity is a curvature of time is that a wave of light can lengthen and lose its intensity due to the influence of massive bodies. So, if an observer is in an accelerating spacecraft, then in his eyes the wave of light emitted from the bottom point would be elongated relative to its original wavelength. This in turn would cause the color of the light to change from red to blue. This phenomenon is called the redshift of light and is not predicted by Newtonian gravity. In 2016, Professor Andrea Ghez led a team of researchers to observe the blue star SO-2, which came close to the black hole Sagittarius A. If Einstein's theory is correct, then the light wave from the star should have changed its color to red for the scientist's reference point. And the star did indeed glow red, which again confirmed Einstein's gravity. So Einstein's gravity model has made a real breakthrough in understanding the physical process taking place in our universe. At present, it is confirmed by perhaps not all tests of its reliability and reveals many details of time-space. Nevertheless, the Newtonian model can still be a serious competitor for GR. For example, while observing the rotation of disk galaxies in the 1930s, Danish astronomer Jan Oort first noticed that the rotation speed of stars on the edge of such galaxies remains constant, although they should be moving much slower. The solution to this paradox is the hypothetical dark matter first described by astronomer Fritz Zwicky, which surrounds galaxies. According to current estimates, about 70% of the universe consists of 27% dark matter and 5% ordinary matter. However, although dark matter is an important hypothesis for explaining this phenomenon and many others, such as bullet clusters, its existence has not been precisely confirmed so far. On the other hand, a modified model of Newtonian gravity, modified Newton dynamics, proposed by astrophysicist Mordecai Milgrom, can explain the orbital rotation state. There are other rules for objects with much lower acceleration than in our system. Milgrom modified the formula of gravity by adding the constant AO, which defines the critical point for acceleration. So if the acceleration caused by gravity reaches this point, then Newton's laws, which were in effect before the critical moment, will be replaced by the new laws introduced by GR, and the inverse square law that we observe in our solar system would stop working, which will equalize the acceleration, meaning it will not depend on the distance from the center. This theory, in fact, explains the motion of stars and many other galaxies without the presence of dark matter. However, it has several serious problems. For example, it cannot completely exclude the presence of dark particles, since galaxy clusters in the Mond analysis are still characterized by the problem of insufficient mass, which is solved by dark matter. Therefore, this theory, although it offers an explanation for the orbital velocity phenomenon, has, in particular, drawbacks that are still being solved by GR. And finally, the main problem with Einstein's gravity is the inconsistency with quantum mechanics. The main problem between these fields of physics is that GR is based on the principle of causality, while quantum physics is based on probability. Therefore, GR cannot work at the level of quanta, and quantum mechanics cannot work at the level of macroscopic objects, since an observer will know where a large physical object is located and how fast it's moving. There's no superposition state for it. The only solution to this problem can only be to develop a new theory of quantum gravity that would explain the interaction of objects and fundamental particles simultaneously. Despite some problematic issues, Einstein's repeatedly confirmed gravitational model is still the basis for modern research, regardless of its age. We cannot say whether GR will suffer the same fate as the law of gravity, but the coordination of the model of the world according to the theory, along with other areas of physics, is necessary without understatement for the whole of science. So since we do not yet have a new gravitational theory, we can summarize with some confidence that gravity is not a force.